We'll now continue our discussion of section 4.3 and discuss ways to locate real zeros of polynomials. We're going to look first at what is called an upper or a lower bound of the zeros. When we're discussing this, if we have an upper bound of the zeros, we're saying that there's no zero that's any larger than this upper bound. Or if we have a lower bound, we're saying that there's no zero that's less than this lower bound. So it gives us a range of numbers that could be used for the zeros of the polynomial. We're going to use synthetic division to find the upper and lower bounds. All right, we have a polynomial. We need a to be a negative number, and we need b to be a positive number. Then we say that no real zero of f is larger than b. Right? Remember, b is your positive number. B is called your upper bound. If the last row in the synthetic division contains no negative numbers. And we say that a is the lower bound. So no real zero of f is smaller than a if the last row in the synthetic division has entries that alternate in sign. All right, and they note that zero can either count as positive or negative. So let's look at an example to see how this works. We want to use synthetic division to identify the upper and lower bounds of the real zeros of f of x is equal to 2x to the third plus 3x squared minus 14x minus 21. So we'll begin by choosing a positive number and look at that as a potential upper bound. Now, you can choose any positive number that you want, but you're better off to choose a smaller positive number. So let's choose 2. All right, and I'm just randomly picking 2. It is positive and it's relatively small. We're going to do synthetic division with the 2. So we're going to divide 2 into 2, 3, negative 14, and negative 21. So we're going to drop this 2 down. We're going to multiply. 2 times 2 is 4. We'll add to 3, give me 7. 2 times 7 is 14. Add to negative 14, we get 0. 2 times 0 is 0. Add to negative 21, we get negative 21. So remember what our rule says. We're checking for an upper bound. And it says we have an upper bound if the last row in the synthetic division contains no negative numbers. Well, we do have a negative number in our last row. And so what this tells us is that 2 is not the upper bound, which means that there is a 0 that is bigger than the 2, or at least there could be. So now what we want to do is we want to try a different positive number. We want to try something a little bit bigger than 2. So we might look at it and say, okay, what if we tried 3? So let's do the same thing, but let's do it for 3. So I'm going to do synthetic division with the 3. So again, we're going to drop this 2 down. 2 times 3 is 6, and we'll add, giving me 9. 3 times 9 is 27, and we're going to add, which gives me 13. 3 times 13 is 39, and we're going to add, and we get 18. So notice now that we have all positive numbers across the bottom, which is what we wanted for the upper bound. So we can conclude that 3 is an upper bound, that there is no 0 for the polynomial that is bigger than 3. All right, so now that we know the upper bound, let's work on the lower bound. So we want to do the same thing. We want to test a negative number for the lower bound. And again, you're better off to select something that is relatively small. So maybe I'll try negative 3. So I'm going to do negative 3 and do its synthetic division into that original problem, which remember had a 2 and 3, a negative 14, and a negative 21. And here for the lower bounds, remember that you're looking for an alternating sign from positive to negative across your bottom row. So I'm going to drop the 2. Negative 3 times 2 gives me negative 6. And I'm going to add, giving me negative 3. So that's good. We have an alternating sign. Negative 3 times negative 3 is 9. And we're going to add. And that gives me negative 5. Okay, right now I know that negative 3 is not a lower bound because this sign did not alternate across the bottom. So that's not going to work. So we want to go to something else. And remember, you want to use something that's smaller, but you want to keep it relatively small. So I might move to negative 4, and let's try negative 4. Okay, so we're going to drop that 2. Negative 4 times 2 is negative 8. We'll add, giving me negative 5. Negative 4 times negative 5 is 20. We'll add, giving me 6. Negative 4 times 6 is negative 24. And we'll add, and we'll get negative 45. Okay, so this one worked out well because we can see that the signs alternate across the bottom from positive to negative. So negative 4 is the lower bound, which means that there is no 0 that is smaller than negative 4. So we now know that all of the real zeros for this polynomial are between negative 4 and positive 3. Okay, so how do we use this? So we're going to take the results in conjunction with our rational zero theorem, and we're going to find these actual zeros for this polynomial. So remember that your rational zero theorem says that you're going to identify this negative 21 as your P, and this positive 2 leading coefficient as your Q. And you're going to look at factors for each one. All right, so if I'm looking at the P, I'm asking myself, how do I make negative 21? I can do negative 1 times positive 21. I can do positive 1 times negative 21. I can do negative 3 times 7, or I can do positive 3 times negative 7. So my factors would be plus or minus 1, plus or minus 3, plus or minus 7, plus or minus 21. All right, let's do the same thing for the 2, for the Q. So I could do 1 times 2. I could do negative 1 times negative 2. So my factors would be plus or minus 1 or plus or minus 2. All right, and then remember that your possible rational zeros are going to be found by doing P over Q. So we're going to take all of these P values and put them over 1. So they're not really going to change when I do that. And then we're going to take them all and put them over 2. So we'll get plus or minus 1/2, plus or minus 3/2, plus or minus 7/2, plus or minus 21/2. So these are my possible rational zeros. However, we know that there's no 0 less than negative 4, and there's no 0 that's bigger than 3. So this will allow me to eliminate some of those possible rational zeros. All right, so let's do that, and let's get a kind of a combined list. All right, so let's think about, tell you what, let me write them out up here at the top so we can look at each one. All right, so we have 1, 3, 7, 21, 1/2, 3 halves. I'm just copying them from the last slide. 7 halves and 21 halves. We also have the negatives of all these numbers. Okay, so these were our potential rational zeros, and we're now saying that there's no zero that's greater than 3. Okay, so that allows me to eliminate the 7 and the 21. It also allows me to eliminate the 7 halves, because that's 3.5, and the 21 halves. Okay, and then there's no zero that's less than -4. So -7, -21 are both out. -21 over 2 is out. So let's make a list now of what we have left. So our potential rational zeros, we have 1, 3, 1/2, 3 halves, -1, -3, -1/2, -3 halves, and -7 halves. All right, and so once we have that list, so essentially what we've done is we've taken this big list of potential rational zeros, we've used our bound theorem to eliminate some of them. So now we can use synthetic division to test your potential rational zeros. Now again, the book is suggesting that you randomly select one of the numbers in our list and start testing until you find something with a remainder of 0. We talked about in the last section about instead of testing all 9 of these numbers, using your calculator to make sort of an educated guess as to what to check by graphing and looking at the graph of that function. So let's test. As I do that, it looks like -3 halves might be a reasonable choice. All right, and so that's where I'm going to start. I'm going to start by checking to see whether -3 halves is a 0. Remember that we're going to check that by doing synthetic division. So we're going to divide right back into that original polynomial. Use your calculator if you need to with these fractions. So we're going to drop the 2. -3 halves times 2 is going to be -3, and we'll add and get 0. -3 times 0 is going to be 0. Add and we get -14. -3 halves times -14 is going to be 21. Add and we get 0. All right, so remember that the fact that you get a 0 for your remainder tells you that -3 halves is a 0 for your polynomial. If you got something else, you would need to pick a different number and try again. So what does that leave us with? Our original polynomial started with a 3rd power, so this 2 is going to go with the 2nd power. So we have 2x squared plus 0x minus 14 is equal to 0. We can solve that to find our remaining zeros. So I can add 14 to both sides. Gives me 2x squared is equal to 14. Divide both sides by 2. That gives me x squared is equal to 7. Take the square root of both sides. I get x is equal to positive or negative square root of 7. All right, so where are our zeros? We have x is equal to -3 halves, and we have positive square root of 7 and negative square root of 7. All right, the last thing that we're going to look at in this section is what is called the intermediate value theorem. This says that if you have f of x being a polynomial and a and b are real numbers such that a is less than b, if f of a and f of b are different in sign, then there is at least a point in between where you have a 0. Okay, so let me show you with a picture what this is saying. All right, so you have a graph of a polynomial function. You have a point A, which is here. Okay, if you go out to A and drop down to the graph, you're here. And this is going to have a negative sign because it is lying below the x-axis. All right, and then you go out to the B and you find your graph above or below the B, and your graph is up here, and this has a positive sign because it is above the x-axis. And so the intermediate value theorem says if you have one that's negative and one that's positive, that it has to cross the x-axis at some point in between. And if you think about it, that only makes sense. If you've got one negative and one positive, somewhere in between, it had to go across that 0 line to change the sign. All right, so let's look at this with an example. It says for f of x is equal to x cubed plus 3x minus 7, show that there's a 0 between 1 and 2. So to use your intermediate value theorem, all you really need to do is you need to calculate f of 1 and f of 2 and show that they have different signs. So if I plug 1 into my function, I'm going to have 1 to the third plus 3 times 1 minus 7. So I have 1 plus 3 minus 7, which is going to give me negative 3. And then I plug 2 into the function. 2 to the third plus 3 times 2 minus 7. We have 8 plus 6 minus 7 gives me 7. So since you have one that's negative and one that's positive, you have to have a 0 in between. Okay, so we could say since f of 1 and f of 2 have different signs, we have to have a 0 between 1 and 2. Okay? All right, and then the last part says find an approximation of the 0 to the nearest tenth. So you know that that 0 is somewhere between 1 and 2. So what you want to do is you want to pick a different number somewhere in between 1 and 2 and plug it in. All right, so I'm going to go at the halfway point. I am going to plug in 1.5. So we already know, I'm just going to write this down from the last slide. We already know that f of 1 is negative 3 and f of 2 was 7. So now we're going to try something in between. Let's try 1.5. So I'm going to do 1.5 to the third plus 3 times 1.5 minus 7. And you may want to use your calculator here to estimate what this is equal to. We will get 0.875. Okay, so if you look at that, this is positive. So if we had used, we're going to ignore this for a second. If we had used f of 1 being negative 3 and f of 1.5 being positive, so we know that there was a sign change between f of 1 and f of 1.5. So the 0 has to be between 1 and 1.5. So we've sort of shrunk that interval where the 0 actually is. All right, so let's try it again. Let's pick something else between 1 and 1.5. Notice how small this number is, which tells me that we're getting close. Okay, I mean that's the height of the height of the number above the x-axis. So if I'm at 0.875, I am pretty close to the x-axis. So I'm going to try 1.4. So I'm going to plug in 1.4 to the third plus 3 times 1.4 minus 7. And again, use your calculator for that. And we're going to get negative 0.056. Okay, so look at this now. F of 1 was negative, f of 1.4 is still negative. So we have not found the 0 in between 1 and 1.4. However, if I look at from 1.4 to 1.5, I'm seeing that sign shift. 1.4 was negative, 1.5 is positive. So I know that my 0 is in between 1.4 and 1.5. All right, so now I need to pick out one more point and try to narrow it down. We're trying to find our 0 to the nearest tenth. All right, so I'm going to go right in between these two, and I'm going to calculate f of 1.45. That's halfway in between 1.4 and 1.5. So I'll do 1.45 to the third plus 3 times 1.45 minus 7. Plug it in my calculator. I'm going to get 0.3986. Okay, so what does this tell me? This tells me that my 0 is not in between 1.45 and 1.5. Okay, not in between those two because they're both positive. But it is in between 1.4 and 1.45 because here we have a sign change. So I can conclude that my 0 is between 1.4 and 1.45. Okay, and if it's somewhere in between that and we're rounding to the nearest tenth, it's going to, regardless of what it is in between those two numbers, it's always going to round back down to 1.4. All right, so I can conclude that my 0 rounded to the nearest tenth is 1.4.